Good afternoon, sir. Dr. Raju.
Yeah, good afternoon. Good afternoon to everybody.
Thank you. Thank you for joining once
Yeah,
again.
it's my pleasure. Thank
Good
you.
afternoon, Bojan. Professor Bojan, good afternoon.
Good day or good afternoon to everybody. Regards
Yes,
from very
yes,
warm
yes.
Croatia.
Thanks,
Hope that
thanks
you
for
are fine
joining.
and that
Thanks
is
for
a little bit
joining.
cold.
Thanks for joining. So,
My pleasure.
so Dr. Shahu, I would like to introduce our faculty convener of this program, that is Professor Dr. Shati Prasad Shahu. So, Shahu and also Professor Bulu Madam. Bulu Madam will join in a second.
Yeah.
So, Dr. Shahu, shall we start?
Yeah, I think Bhumika. Hello, Bhumika.
Your voice
Yes,
is not
sir.
so clear.
Hello,
Yes,
Yeah.
yes.
Bhumika. Yeah.
Yeah,
Yes, sir.
shall we start then? Bhumika, are you here?
Yes, sir. I'm here.
Okay.
Not.
So I think we will start because already we have left 4 minutes extra.
Yeah.
Okay, fine.
Okay,
And
go
let the
ahead.
other people join.
Yeah.
Bhumika, please.
Yes, sir. A very warm good afternoon to all the delegates and participants. First of all, I would like to extend my sincere greetings on behalf of South Asian Institute for Advanced Research and Development. And we are obliged to have this international webinar in our institution on geospatial technology and water resource management. The most valuable natural resource on the globe is water, which is crucial for human civilization, living things, and natural environments. It is also used as an inextricably in the activities related to agriculture, industry, the home, recreation, and the environment. India makes up more than 18% of the world's population, and yet it only possesses 2.4% of the planet's surface area and 4% of its renewable water resources. Due to unequal distribution over both time and place, there are further restrictions on the amount of water that may be used. The prospect of water stress is very real for India as a result of the country's rapidly urbanizing population and the tremendous pressure this places on the country's limited and vulnerable water supplies, which are already stressed and depleted at the critical levels of underground water. For the reduction of poverty, the preservation of the environment, and long-term economic growth, integrated water management or the coordinated development and management of water, land, and associated resources is essential. Due to its ability to allow for the geographical identification of water resources, significant issues, and more objective characterization of priority activities, geospatial technology has been proven its usefulness in water management. Accurate knowledge of natural resources is the most fundamental and essential condition for making the best use of scarce water resources. We require data or information on variables like rainfall, the availability of surface and groundwater resource, maps of land use and land cover, elevations, slope, land surface, temperature, evapotranspiration, biomass, etc. Not only information is needed, tools are required to properly analyze such information for planning purpose. It's here geospatial information and technology such as remote sensing, visualization, GIS, LIDAR, etc. can play a crucial role. And here a topic comes into light. I would like to express my sincere gratitude to Dr. Biswajit Roy Chaudhary, the chairperson of SAIARD, for giving us this chance to hold this seminar at his institution. Thank you, sir.
Thank you, Bhumika, and thank you to all the resource persons, especially our guest of honor, Dr. P.V. Raju sir from NRSC Government of India, and all the resource persons from my friend Dr. Bozan from Croatia, and also Dr. Prabhakar Sharma, Dr. Mandal, Dr. Lanka, and Pulokesh Das, Dr. Pulokesh Das, for this 2 days international conference or confluence, you may say, on the utilization sustainable water resource management and the geospatial technology. So actually on behalf of IIGST and SAIARD platform, I heartily welcome first of all the participants and to all the delegates, those who have joined from the different corners of the world. You know that IIGST is a part of SAIARD institution, and from the very beginning of our institution, we are mostly focusing on the application of geospatial technology in different aspects. And obviously, water is one of the major parts of this. And in this figure, today we are going to organize this webinar, and where I'm really thankful that within a short span of time, you have all joined and we have all given your kind consent to be a part of it. And now you are associated with us as one of our family member of IIGST platform. So this webinar mostly, as you know, that water resource is a very crucial part in recent days, and government of India has launched several programs related to the water, and one of the major issue is the Jal Jeevan Mission. And this conference, hopefully, I believe that this conference will definitely bring some outputs and definitely highlighted some issues related to the water resource as well as its application of as well as the application of geospatial technology for the better management of these natural resource. And our all students, our research scholars, even the faculty members, research scholars from the different academic institutions, those who have joined, hopefully they will get some extra inputs with this through this conference. So with this, I will no longer extend my version today because we are mostly seeking to know about the concept, and also we are going to live a recorded session and we will share it to our YouTube platform as that other people can able to know, those who will not be able to join today. So with this, once again, I heartily welcome. I thanks to all of you and all the participants, and last but not least, my colleagues, Dr. Shahu, Ms. Guru Bashak, and Mr. Asha Akash, and also Bhumika for coordinating this program. Thank you. Over to you, Bhumika.
Thank you, sir. We are obliged to have Dr. P. Venkatraju, scientist by profession, G, and group director from the Department of Space Water Resource Remote Sensing Application for here today. Also, we have Dr. Bojan Durin, an associate professor in the Department of Civil Engineering at the University North in Varasagan, Croatia. Dr. Prabhakar Sharma, an assistant professor at Nalanda University in Bihar School of Ecology and Environment Studies, as our guest of honor for today. We are also pleased to welcome Dr. Kartikeya Ganga, assistant professor at Indian Institute of Technology, Bombay Center for Studies in Resource Engineering, India. Dr. Uday Mandal, scientist at Indian Institute of Soil and Water Conservation, that is ICAR, Indian Institute of Soil and Water Conservation, located in Dehradun, India. Sustainable Landscapes and Restoration Senior Project Associate, World Resource Institute, New Delhi. I heartily welcome Dr. Pulkesh Das as our distinguished speakers for today. With this, I conclude myself, and at last but not the least, I would like to welcome and thank all the participants for joining this webinar. Now, I would like to invite Dr. Sahu, the faculty of IIGST, as well as the convener of this event, to welcome our guests. Over to you, sir.
Okay. Thanks, Bhumika. Thank you, everybody, for joining this international webinar on geospatial technology and water resource management. It's a very important for future water resource planning and management purpose, because now we are facing the water crisis problem over the world. So remote sensing and GIS technique can be solved this kind of problem. That's why we have arranged this kind of webinar on geospatial techniques and water resource management. So I would like to welcome to our guest of honor, Dr. P.V. Raju, scientist and group director, Water Resource Remote Sensing Application, NRSC, ISRO, Department of Space, Government of India. And I would like to welcome to our honorable guest, Dr. Bojan Durin, Associate Professor of Civil Engineering, University of North, Baradin, Puratia. And another honorable guest, Dr. Prabhakar Sharma, Assistant Professor, School of Ecology and Environmental Studies, Nalanda University, Bihar, India. And Dr. Karthikeyan Lonka, Assistant Professor, Center of Studies in Resource Engineering, Indian Institute of Technology, Bombay. And another honorable guest, Dr. Uday Mondal, Scientist, Hydrology and Engineering Division, ICR, Indian Institute of Soil and Water Conservation, Dehradun, India. And another honorable guest, Dr. Pulokesh Das, Senior Project Associate, Sustainable Landscape and Restoration, World Resource Institute, New Delhi, India. And thank you everybody for joining this webinar. I think it's a very good international webinar and for water resource management using remote sensing and GIS techniques. This kind of webinar can be held to the policy making purpose for future planning and water resource management purpose. Thank you all. Thank you. Over to you, Bhumika. Bhumika.
Yes, sir.
Yeah.
Thank you, sir, for your words. Now, I would like to invite Dr. P. Venkatraju, the scientist from G and Group Director, Water Resources Remote Sensing Application Area, NRSC, ISRO, Department of Space and Government under the Government of India to address us and enlighten us on the topic of the overview of geospatial technologies for water resource and management. Over to you, sir.
Thank you, Bhumika, and good afternoon and greetings to everybody. It's my pleasure, and I thank profusely Mr. Rai Chaudhary, Dr. Rai Chaudhary and IIST staff for giving me this opportunity to share my views and the expertise at NRSC with all the distinguished participants here. Greetings to Dr. Bhujan, Dr. Prabhakar Sharma, Dr. Karthikeyan, Dr. Uday Mandal, and Dr. Pulokesh Das, and also greetings to all the participants who have assembled online for this very important conference which is being held by IIJST. I compliment the organizers for the very important topic they have chosen, which is very pertinent to the current scenarios what the entire world is facing with managing water resources in a very efficient and sustainable way. Taking forward, given the topic that is given to me on sharing the ISRO's experience on remote sensing and GIS in water resources sector, I have made a brief presentation. I would like to share my screen. Can I do that? Is my screen visible?
Yes, sir.
Yes, we can see it. Yeah.
Yeah. Thank you. So once again, good afternoon and greetings to everybody. The presentation I'm going to share with you, apprise you on the remote sensing and GIS applications in water resource sector, more specifically providing few examples of NRSC in ISRO experience, as well as providing some important data points that are available openly through various web platforms, which water resources sectors, people who are managing or looking for water resources sector management can look after. Just to give a price to start with, we all know how important the water resources are for our daily living. And if you look at the water resources of India, as per the recent latest estimate of Central Water Commission, which is completed in 2017 study, the overall annual precipitation, mean annual precipitation is 3880 BCM, out of which the water availability is designated as 1999 BCM. And of course, the utilizable water is only 1122 out of this close to 2000 BCM, with surface water is around 690 BCM, and replenishable groundwater is around 432. And as we all know, as the teeming population is is reducing the per capita availability, even though the estimate is given 2001 here. Now with the current estimate of 130 crores, now the per capita availability has further decreased in India. And the demand is steadily increasing, going to various reasons. And as you know, you might be aware, India is the largest, having registered highest, net irrigated area in the world, with around 63.19 million hectares. And out of 140 million hectares of total irrigation potential, ultimate irrigation potential, the net irrigation utilization is in the order of 63 million hectares. So India has made significant progress in harnessing the water sources potential and its use for its various sectoral utilization, but still challenges are many. Just to list out few challenges, as we know, water is increasingly becoming scarce. When they say scarce, because it is changing its temporal and spatial dimensionality. It is not available when we need in terms of its utilization. It is not available at the location where it is more demanded for. Because of a high increasing variability, a high uncertainty, it is associated with the water availability. And due to increasing population or increasing industrial revolution and many aspects, the land and water resources are reaching their exploitable limits. And there is a severe competition among water use sectors. Now, if you see agriculture in India, which uses more than 85% water for agriculture in India, is having very low water use efficiency, whereas the industrial sector and other productive sectors are at a higher efficiency, are putting serious threat demand to water, which is posing serious challenge to agriculture sector to use water more efficiently, more judiciously, so that the water requirements of other sectors are also equally met with. And owing to industrialization and also owing to urbanization, the water demand is increasingly becoming localized. That's another serious challenge most of the developing countries are facing. As the cities are growing, the urban sprawl is increasing, the requirement of protected water is becoming more geographically concentrated. More in general, as we all know, these cities are at a higher elevation, which are not always on the river beds. Their water has to be brought from somewhere where water sources are scarce, and that is becoming a localized, geographically concentrated demand towards cities and towns, which is every city is posing a challenge. And also, the available water is also becoming inadequate for various reasons. It is owing to increasing population or increasing the industrialization or various reasons. And we all appreciate that we are facing climate change impact. We are already perceiving, and also we are victims of that. The water availability is changing as a result of these changing climate conditions. We are experiencing very high intense rainfalls, and extended long dry spells are prevalent more frequently. And also as a result of increasing temperatures and dry periods, the water demand is also increasing, and we all know how water disasters are increasing day by day. Today, entire Brahmaputra valley is under severe floods in India, and all these challenges are further complicated or compounded because we do not have a proper decision support systems where the data pertaining to water and its interrelated parameters is collected but not transformed into an informed decision. most of the times its data is collected for an archival purpose rather than to convert this data into an informed decision. There is a major challenge the water sector is facing with. So with this, to overcome this kind of a constraint and challenges, there is a need to have information about the water sector. I briefly listed out some of the information needs for the water sector. Because water is a resource which is generally denoted at a regional scale, and it is used at a local or individual levels. So naturally, when you want to assess the water requirement, water use, water availability, you need a lot of information about terrain and the contributing precipitation, how much is the rainfall, how much is going to be the forecast of precipitation, and how this availability is varying spatially and temporally, and especially where the rivers which receive significant snow and glacier melt, what are the snow cover dynamics, what is the glacier retreat that is happening, and what are the options for harvesting the water resources at the in situ level, what is the soil moisture status. So and so there are so many the information needs are there to manage water, so that you convert this information into data to inform decision, so that water resources can be done in a most optimal and sustainable way. Looking at space sector today, it is a large transformation has taken place in space sector. If you see Earth observation data observation capability, it has transformed into multi-dimensional, multispectral, with a greater observation capability, and many Earth observation operators, satellite operators are making this data open with a free access, and this data is being collected and through entire spectrum of electromagnetic regime, covering various aspects of its interaction with the land cover features, optical, micro, and with a greater high temporal revisit capability, and with a regional level monitoring, capturing, and daily time steps to very local, even up to field scale, we can obtain information from the Earth observation data. And this is also has got a new dimension. It is being supplied on a demand based. And there are various complementary sources have emerged, like UAV drone platforms, aerial platforms, which are providing demand based, as well as bringing it to almost at the field scales. And also another major feature of these recent past satellite remote sensing capability or Earth observation capabilities, reduced latency and analysis ready products. If you see Landsat 8, Landsat 9, Sentinel, entire Copernicus suite of satellite data availability, even Indian remote sensing satellite data also, ISRO is making efforts. As soon as the data is acquired by the satellite, within no time, within 24 hours, it is hosted on the web, and with the analysis ready, products are available, orthorectified reflectance products are available. That means users are ready to consume, users can readily consume these products. And a lot of biogeophysical parameters are extracted from this multi-spectral information, which will help in characterizing the land cover features in their spatial and temporal characteristics. And many web-based EVO data analytics platforms have come up, which are open-ended with data cubes, with community algorithms, with a shared GIS data resources. These are significantly rather equipped all the remote sensing and GIS fraternity in exploiting the full potential of Earth observation data and remote sensing data capability for deriving water resources related information, not restricted to only water resources, all the natural resources related parameters extraction and transforming them into information to decision support system. And if you look at the water resources sector, satellite data today, it is providing all facets of all entire hydrological cycle related parameters are being captured by satellite remote sensing technology, right from the precipitation to when it is falling and getting collected on the surface as a surface storage or as a snow cover, and using altimeter data, what is the elevation of a river or a reservoir, and when it is stored as a soil moisture in a soil strata, we are able to retrieve using passive and active radiometers, and also using energy computation, thermal and microwave data, we are able to compute the energy exchanges that are driven by the atmospheric demands, that in turn you can estimate evapotranspiration and other aspects using optical, thermal and radiometer data sets. So there are various components of hydrology and as well as water related parameters are readily retrievable either directly or indirectly using satellite data in support of water resources management. In my next few slides, I will be sharing with you quickly on some of these products, what are they available from the remote sensing earth observation platforms, what are the globally available free data sources, because specifically I organized this particular presentation to, because this IIGST students, trainees, it will be very useful for them to know these sources of this open data related to water sources. I have organized, presented, incorporated all those aspects in my presentation. Moving forward, I'm not going to go into these details. I will have organized, as I mentioned, on each of these water resources related parameters, how the principle, how it is being estimated from remote sensing, and what are the data sources, how this information can be used to translate this information, primary information, to water resources related parameter extraction. That a few examples I've incorporated so that it can be understood how today these parameters that are observed or captured from remote sensing platforms are used for generating water resources related information and their applications. As we all know, precipitation is the main driver and source of all hydrological processes. And conventional estimation of rain gauge is sparse and it's a point based, and always the aerial estimates are will have a lot of uncertainty. Today, using micro platforms, Doppler weather radars, spatial and temporal rainfall estimation is very routinely estimated by geostationary platform. One of the classic example today, taking forward previous satellites, you get spatial estimates from remote sensing platforms from various platforms. For example, earlier TRMM was there, which was providing spatial estimates of precipitation. Now GPM satellite constellation, almost it provides an hourly precipitation for the entire globe at 0.1 degree. It has multiple data sets with different latency, which each one having a different accuracy levels, which are again merged with observation data to improve the spatial the accuracy of the reliability of the precipitation estimates. These are the few global sites which provide a near real-time or observed precipitation data, spatial precipitation data sets for the entire globe or for selected regions, which form the primary input for any water resources related applications. Even IMD, Indian Meteorological Data Organization, also provides on a daily basis 0.25 degree rainfall information for the entire country using a merged algorithm which uses more than 6,000 observations of AWS or ARG data with GPM satellite-based precipitation data. A merged product is generated on a real-time basis, and it is hosted on their website and freely downloadable. And these data sets help us in quantifying the various hydrological fluxes. For example, this particular example, what I'm showcasing here is daily this precipitation and other meteorological data. NRSC has incorporated into a national level hydrological modeling framework where at two resolutions, 5.5 kilometers and 16.5 kilometers, 3-minute and 9-minute grid level, daily surface runoff, profile soil moisture, and evapotranspiration are estimated on a daily basis with a T-2 latency. We are estimating and hosting on Bhuvan site. So one can know where the precipitation induced surface runoff, soil moisture variations, and resulting evapotranspiration consumption is happening across the country on a daily basis systematically at the grid level. While this data sets not only uses the near past meteorological data, it is also the forecast, weather forecast is also ingested into the modeling framework, and at T+3, next 72 hours forecast is also incorporated and they are web published. These data sets have many utilities. For example, soil moisture data can be used to estimate what is the irrigation requirement. This surface runoff can be used for estimating the water availability and inflows into reservoirs, river discharge, and evapotranspiration. It can be used to various aspects, including agriculture productivity and primary productivity. As we all know, satellite data, the primary information that can be derived from satellite data is the surface water spread, because water that gets collected as a result of precipitation translating into surface runoff, it flows through the streams and river channels and gets collected to local depressions, surface water bodies, which are either man-made or naturally occurring low water bodies and tanks and water bodies. So entire country NRSC has developed an automated algorithms as we receive the satellite data through the satellite data acquisition process chain. We have developed algorithms to process the satellite data and retrieve surface water spread for every water body. More than 16.3 lakh water bodies across the country have been digitized, and their water spread information is extracted on a periodic basis without any manual intervention. As you can see here, the animation which is shown here, Sriram Sagar project, it is a part of Telangana state on Godavari River. This particular reservoir is constructed, and its surrounding areas, you can see how the temporal dynamics of surface water spread are directly captured from remote sensing. This is how we are hosting the data on a water body information system on one platform, where for different size of water bodies, the various frequency of water spread information is available, and it is being used for various applications to estimate the surface storage in major and medium reservoirs, to know what are the perennial water bodies which can be used in summer season for fisheries cultivation, and also for hydrological drought assessment. There are many applications which are accessing these data sets as part of Blue Revolution and many national programs. Data is very widely used. Similarly, there are, for example, this is the output of one of the output, how you can know for one particular reservoir how the water spread varied in different time periods. Since this data is available since 2012. There are similar global efforts providing water spread information on near real-time basis from the satellite data. This is one example where the Water Watch using Earth Engine, they are providing for entire globe. This is a snapshot for India. And while the surface water spread available information is completely automated, it is hosted. We also carried out the water bodies, the glacial lakes inventory in the Himalayan region. And another important source of water resources, as we know, is the snow cover. Snow cover information is very crucial because the snow cover extent and its persistence varies from year to year owing to meteorological, local and regional meteorological conditions. And for example, in India, Indus, Ganges and Brahmaputra rivers, almost more than around 20% of their annual flow is as a result of snow melt from the transboundary catchment. So if you look at these catchments of these three important rivers which are perennial and which receive huge amount of snow melt in summer season, more than 60%, around 55% of their catchment is not within India. So, and highly rugged terrain, there is no way we can know what is the amount of snow, extent of snow cover and how much it is going to result into snow melt during summer seasons. Satellite data is the only source to know the intra-annual and inter-seasonal variations in snow cover. NRSC regularly monitors the entire snow cover in Himalayan region, and we capture their interannual variations and generated a energy balanced model based snow melt runoff estimates for entire Himalayan region of our Indian river basins. So this is a typical example how from 2019 to 2020, how the interannual changes in snow melt occurred across the Himalayan regions, clearly indicating where the compared to 2019, where there is an increase in snow melt rate, where there is a significant decrease in snow melt rate, and this information we are translating into melt runoff into the rivers, inflows into the major reservoirs, and river discharge at prominent locations, so that this information is fed for the water resources managers, both for the reservoir management community as well as the concerned state water resource department can make use of this information for their water resources management decisions. While these examples, they speak about the water resources availability in terms of surface water, in terms of snow cover and resulting snow melt, another major contribution from remote sensing is the water use, because all the water that is put into agriculture consumption goes as an evapotranspiration process, and evapotranspiration is very difficult to measure. There are various empirical and instrument-based estimates of evapotranspiration. I have got another 10 minutes. Mr. Chaudhary,
Yes, sir.
I can take another 10 minutes, isn't it?
Yeah. Go ahead.
Maximum 10-15 minutes I'll take.
Okay.
So evapotranspiration process is very difficult to measure spatially. Local point estimates are done using some field experiments, otherwise some using instrumentation like eddy covariance flux towers or scintillometers or lysimeters, an experiment based. But estimating actual water use is a very difficult on a spatial basis. For example, you want to know in an irrigated command area, you might have measured how much water you have let out for irrigation water delivery from the discharge from the canals. But what exactly, how much is actually used for crop water, evapotranspiration, it is very difficult to get a spatial estimates. But today, remote sensing platforms with their observation capability extending from optical to thermal to microwave, the energy balance approach is one of the very widely used because evapotranspiration is mainly driven by the energy exchange at the land surface. Satellite observations are capable of computing the residual energy because what is observed from the satellite data, the surface reflectance, and also the brightness temperature can be translated into into net radiation, and using this latent heat flux formula, we can estimate what is the actual amount of energy consumed by the land surface, which can be, and what is the incoming energy. Using energy balance computations, we can translate these energy units into what is the latent heat flux, which in turn is nothing but the water that is consumed or transpired either evaporation or through transpiration process at the land surface level. And NRSC also established an operational framework using various data sets right from INSAT to Suomi NPP, and also integrating with field observation data. On a daily basis, we are estimating the actual evapotranspiration at a 3-minute grid level, that is 5.5 kilometer grid level for the entire country. Of course, it has limitation because all these energy balance computations are feasible when there is no cloud cover. So we are developing alternative methods during monsoon season, but nevertheless, during clear sky conditions, we are able to build this database for the entire country, and this is being done since 2019, and we'll extend it to for historical year also. And similarly, there are various global platforms which are providing. There is a national global consortium called OpenET, which is integrating multiple approaches of this satellite-based ET estimation like metric, Sebal, simple surface energy balance programs, and other applications, bringing all of them using all the openly global satellite data systems. They are generating a open ET platform which will provide a consistent evapotranspiration product, global evapotranspiration product for the use for the all water resources sectors. In fact, for every sector, which can this, because this is one of the very important useful information, because once you know evapotranspiration, it has many applications, like you can do water balance computations, you know where how much canal water is used, how much groundwater is potentially exploited. So, and also for climate change studies, it has many applications. And these are the few global open data sets of evapotranspiration. I'm not going to read out them. The second, another important observation capability from remote sensing, which is very important contribution it is making in water resources management, is the soil moisture. As we know, soil moisture is a very important variable in land surface hydrological processes, because soil moisture controls the evaporation process, the transpiration process, and also it's the energy interaction with the land surface and albedo interaction. And soil moisture estimation, similar to evapotranspiration, field-based is a point-based estimates, doesn't provide the regional spatial variation, whereas satellite observations, especially through micro regions, have got a significant capability for soil moisture retrieval. Even though visible region like SWIR band, shortwave infrared, as well as middle infrared have capability, but not a quantitative soil moisture cannot be retrieved, whereas microwave satellite data has got the potential to translate soil moisture into quantitative. Today, if you see passive micro remote sensing program satellites like SMOS, AMSR2 with GCOM on GCOM platform, SMAP, These satellites are providing a global near real-time surface soil moisture estimates almost for the last 3 decades. Such information is available. Even though passive micro remote sensing is providing, because of its obvious limitations of a large footprint, it is providing at a coarse resolution, but it's worth capturing this information, and coupled with active micro remote sensing techniques, there are many products which are translating this coarse resolution to fine resolution soil moisture products. These are the few examples which are using with soil moisture retrievals and translating the soil moisture by comparing with soil water holding capacity. There are many value-added products can be generated, like what is the moisture availability index and what is the irrigation demand. There are many applications are there using this soil moisture as a primary input in water sources related applications. These are the few examples. So at NRSC, we are generating the soil moisture availability, integrating satellite as well as model computed soil moisture products. These are the few examples of global soil moisture products. Another major contribution, I'll take another 5 minutes. Major contribution from remote sensing is hydrological modeling is the backbone of water sources management related aspects. So hydrological modeling requires many data sets, either coming to precipitation, we call it meteorological data, precipitation, surface temperature, and also land cover, because this land cover will control precipitation response, interaction with the land cover, with the forest interacts differently, a barren land interacts differently. So land use, land cover is very, very important in weather forecast and hydrological models. So there are many parameters that are generated. This table and next sheet, this table clearly demonstrates what are the various parameters that are derived from space technology, and what is its category, and how they are used, in what context it is useful in hydrological modeling. I have listed here. I'm not going to read out. These are the few contributions from remote sensing, how it is helping in hydrological modeling. And exploiting this particular example, I want to share with this participants. NRSC and Central Water Commission have jointly carried out a national level study for entire Indian river basins. Space-based inputs were used to recompute the water availability in the country, considering last 3 decades of data, both land use, land cover, and meteorological data, and other associated information, socioeconomic data. Now we revised assessment of water availability in the country has been done. While 1993 estimate was 1869, 2017 study has brought out that India water resources availability is 1,999.20 BCM against 3,880 BCM of precipitation. This report is web published. You can verify with the Central Water Commission website, where you get all the further details. This is one of the classic example where remote sensing based inputs are used to assess the water availability at the basin scale. And this particular framework that is developed has brought out a systematic utility, so that Central Water Commission can repeat this exercise at a regular periodicity, which is as per the National Water Mission. Of course, satellite data based inputs, spatial inputs formed very critical, especially digital elevation models, digital terrain models, and precipitation forecasts. They form vital inputs in forecasting water-related disasters. One of the classic example is flood early warning systems development. We have developed spatial flood early warning systems for Godavari and Tapi river basins using all these geospatial data sets. Flood early warning in terms of hydrograph, as well as how much submergence will, what are the areas that are likely to get submerged, what is the depth of inundation is being forecasted for all the floodplains in Godavari and Tapi river basins. This is being operationally implemented since 2019 flood season. This is how the few examples how we are forecasting the likely inundation that is likely to happen as a result of increased precipitation or inflows into the reservoir, inflows into the river. As a river carrying capacity exceeds, what is the likely flood inundation, which villages are going to get marooned, how much is the depth of inundation, what will be the flood hydrograph. We are generating in a completely automated spatial environment flood early warning system. And today satellite data has also as capable of retrieving surface water level heights, satellite altimetry with a very high precision, and using various satellites like JASON and other altimeter data, including Saral Altica, which is a joint satellite with the French CANES and ISRO. Entire in over India, all these altimeter observations are captured. They are pre-processed, and their the surface water levels are web published on MOSDAQ, our own sister organization, Space Application Center, Ahmedabad. They have developed a website, MOSDAQ, in which it is hosted. This is the few examples how on a daily basis, as per the data availability of satellite altimeter, surface water levels both on rivers and reservoirs are web published on Veda's website. This has various applications, right from using it for river discharge stage curves generation, as well as river discharge estimation, as well as simulating what is the, if the river water level is exceeding the danger level, what is the likely flood inundation, it can be translated. Of course, these are the few examples. GRACE recovery experiment, GRACE has provided a new dimension of observing subsurface water use or water availability in terms of groundwater use. There are many studies of that, and we are supporting various national programs as part of water resources. NMCG is one of the profuse user of remote sensing technology, and NRSC, as part of ISRO's internal program, entire groundwater prospects maps are mapped for the entire country at 1:50,000 scale, providing what are the prospects of groundwater across the space and identifying the prospective areas. This is very widely used by rural development wings at the state level and the central level for drilling the tube wells. And using these groundwater prospects maps, the success rate has tremendously increased. This is one of the very successful example of space technology intervention in improving the water management or water source identification. And just as I mentioned in my initial today, the scope or the enabling capability of using satellite-based analytics has tremendously multifold. It has got increased because of these open web platforms using Earth observation data. Many platforms are providing free access of not only geospatial data, also for all the analytics. Complete analytics can be handled using these platforms. These are the few examples, and complementary technologies are further enhancing this regional scale or local scale applications to field scales like airborne or UAV and drone technologies because of their flexibility and easy deployment and demand-based data generation. These are the few examples where we have used drone technology to estimate rather area elastic capacity curves are estimated where a small irrigation tank. And allied technologies like communication technologies in mobile devices, developing a mobile apps, or further supporting both satellite data based applications in terms of ground data, ground truth collection, as well as data dissemination, as well as access, improving, providing governance applications on a very improved scale. And NRSC has developed many informatics, water informatics portal, because one of the major limitations in the water resource sector is providing the information at the right location at the right time. So providing a systematic data access, archival, repository, as well as access as in a systematic basis to all the stakeholders is one of the very important aspect in water resources management. In towards that, NRSC has developed many water resources information portals like India Varies, Telangana Water Resource Information Systems, Andhra Pradesh Water Resources Information and Management System. These kind of information portals are bringing all the water related information to at a centralized, a standard single window platform where all these data sets can be integrated and various product information products can be generated, and decision support system tools can be developed such that entire water resources availability, audit, and also management decisions can be done. These are the few examples. In fact, I would like to bring it to the notice of this particular audience. The T-Waris and AP Varims, which are the joint ventures of NRSC with Telangana and Andhra Pradesh states, have won first and second prizes in National Water Mission Awards of 2019. So this is how NRSA is making use of satellite data for transforming data to information to informed decision, in which in turn is helping various state and central organizations to manage water resources in a much better scientific data driven management rather than depending on a heuristic approaches. If I summarize here, today Earth observation data are very crucial for water resources sector because it is able to capture various facets of water resources parameters and providing various observations, various parameters like precipitation, evapotranspiration, surface water spread, its level, soil moisture, snow related information. And these information, these scientific data provided by satellite data assisting for formulating policies and also for implementing various development programs, and also providing evidence how these development programs are actually making a change in water resources management in terms of increase in irrigation utilization, increase in construction of water harvesting structures, and increase in reduced what you call improving water use efficiency of the irrigated command areas, and also monitoring the physical infrastructure creation. There are various both at a planning stage, development stage, and actually when actual water resources management is happening in all these phases, water space sector is providing very important information and tools are being developed to assist water resources sector managers. And forthcoming satellites like ISRO's NISAR, which is a microwave L-band satellite providing soil moisture, further enhanced soil moisture products like Krishna with a thermal imaging capability, which will further enhance evapotranspiration estimates, like NASA's HIP-3 and China's WCOM provide advanced measurements of for additional parameters in water source sectors, and enormous of data is going to come from the future satellites, and it will usher new challenges. How do we make use of this data? And also it will provide you many new opportunities to translate this information into products which water resources managers can consume and use for their water resources management. Thank you. I'll stop here. I'll take some questions.
Thank you so much, sir. This was brainstorming unit. I would like to invite our participants if they have any question. So I guess no questions. So
Either it is not understood in any fashion, or is incomplete or completely understood. Okay.
thank you so much, sir. This was great indeed, and it has really put us to a thought. Thank you so much. Now, I would like to invite Dr. Bhushan Jurin, an associate professor in the Department of Civil Engineering at the University North in Varazadin, Croatia.
Yeah, Varsity Croatia, I'm here.
Yeah.
I'm prepared. Well, all right, I can share my presentation, just a moment. And you will tell me, can you see my title page?
Yes, sir. It's
All right, just one final check before starting. All right, and you can see all other pages.
yes.
All right, then everything is working. Well, I will put it in presentation mode. Well, it's hard task and very unthankful after such interesting presentation of the professor, which was presenting before me, but I will try to do my best during these 15 minutes. Of course, my presentation is prepared to be quite longer, but I will try to skip some parts which are not so primary for my presentation. Of course, I can leave my presentation, and for all questions, I'm always available. As you can see here, there are my data. I'm from Varsity, Croatia, Associate Professor Banjarin, as colleague has very nicely presented me. Well, let's start. Two main and two only parts of my presentation today will be about the surveying procedures, and after this hydrometry procedures, and you will see one presentation, one insight into the actual and very modern instruments, devices, and of course the procedures for the measurement of the velocity, the flow, and also the position of the water flows. Very depth and very low regarding their depth, and we will see. Well, the maybe most familiar from all of you is the procedure of the measurement of geometry by surveying instruments. You can see it now using GPS. This is very known. to you, and these are examples from my research and also from my scientific and professional projects. And this is well-known technology, of course, and I will skip all of these parts. Some examples of the rivers in Croatia, and also you will see how rivers in Croatia looks like. There are many different parts of Croatia. This is karst area, about my hometown. There are always not quite similar parts. There are also intergranular river beds and such locations, and you will see them. Of course, this is very attractive part of Croatia, very fresh water and quite cold water, must say now. And here are some videos about the measurement. I will skip all of them. Some locations, how the determining of the water profiles is going on. And now also some movies about it. I have to skip them because I'm limited about the time of my presentation. You can see surrounding of the limnograph or hydrological measurement stations. And now usual procedure. Here it is. All right, and now we are using the total station when the GPS signal is unavailable. For example, if you are under some trees, under the bridges, in surrounding of some hilly area, you have to connect with the satellites on the sky, of course. And you can see how total station looks like. Here, some quite not so pleasant conditions for the defining of the water course profile here, but what we can do it because it's quite raw water, and there are some wastewater treatment plants around here, so water is not at a very quality level, of course. Also, some extreme situations here. You can see the very happy face of my surveyor, and now some how to say the scholarly presentation of the transverse profile of the water course, and also
Excuse me, sir?
Yeah.
Sorry to interrupt you, but your slides are not moving.
My slides are not moving. I will use without the full presentations. Thank you for your information. Are now slides moving? Slides are moving now.
Yes, sir.
Okay, I will do in this mode. So sorry, but I will leave my presentation. And this at the first part are quite known technology, so nothing new, especially regarding the audience and the title of this webinar. So sorry. All right, I will continue where I have stopped with my presentation. Some definition of the transversal profile or longitudinal profile for the very simple point of view. Some examples of the obtained results with the measurement of the water course, and you can see how this looks like in the real situation. This is usually obtained by using some CAD program, AutoCAD or something particular and also more appropriate. Defining of the station edges and verticals when we are making some river velocity and flow measurements. Of course, you can see how this is going on. Not so hard task, also very simple, but you have to be concentrated on this, especially in some, I would say, also even dangerous areas where you can find some dangerous animals, some snakes, so you have to be very careful when you're doing this. Some recommendations about it. And finally, now we will come to some instruments and some procedures, and you will now see maybe interesting part. Also, especially regarding some new and very expensive technologies, I must say. For example, hydrometrical wing. Here is the basic of this hydrometrical wing, how such instrument is working. You have analog instruments in most of the time not so mechanical. And for some big rivers, you can see this big construction. And this is small hydrometric link. We have used this on one small river in Croatia in karst area here. And this is the procedure of the measurements. Of course, these are booklets and papers, documentation for writing inside, because this is not so fancy procedure during the mechanical construction of the hydrometrical wing. Yes, and now we can see here how measurement is providing, and now we will skip this part and go to the electromagnetical measurement and also electromagnetical devices. You can see that the procedure is the same, and of course we are moving to the vertical here and to the cross profile of the river. This is one example also, and now finally I will present you very novel, very actual technology, which is the most commonly used, the ultrasonic measuring devices. You can see the basics are on the production and receiving of the ultrasound signals. Also, the same procedure is for the radar device and also to using of the Doppler effect. All right, some theoretical parts I will also skip them. This is some basic part how the measurement procedure is going on to the producing and receiving of the ultrasound waves. And this is the part for the big rivers. You will later see this technology. And this is the part for the measurement in very low and also low rivers, when you can walk into the water course with such device. Here you can see ultrasound measurement device. Acoustic Doppler velocity is the shortcut. We have such device on my department, and also price is only to see about the 15,000 of the dollars. Here's quite expensive, and you can see how this looks like. Here was very rainy day during our measurement, quite unpleasant, quite cold, but also we have done and finished such measurements. And also you can see how this device looks like. This is the part for the controlling for the analysis. Here is the underwater view of the other part of such device, where the sound is here on the underwater level. And this is the procedure of the mounting of such measurement device. Also, you can see here it's very appropriate for using not only for the guys but also for the girls. Here are my students. And also the procedure of the mounting you can see from all point of view. And now you can see also one river in Croatia. These are very, very nice, magnificent views, lots of nature here, but also there is possibility of some snakes, mosquitoes, and some other bugs. Nobody loves such animals, I suppose. And here is the part when we have one project on the water mill, outlet of the water mill, and we have tried also to measure such velocity and flow. Some abandoned water mill. I have many of such projects here. Also, I'm working with students and my other collaborators, and you can see how this water is coming. And also, there are quite bigger velocities than 1 meter per second, and sometimes this is not very pleasant to be in the water. So If you cannot walk through the water, and also if the velocity is too big to be stable on the water, we have other devices. And lately you will see them, also some example of the measurement. To all here you can measure here, but there's always question about the very low temperature, about the raining, about hot air temperature, because usual temperature of water here, we have some measurement a couple of days ago, is about 13 degrees of the Celsius. And on other parts, it will be even bigger, about 20, but this is quite fine comparing with the air temperature. And also some karst area, flesh areas. So this is appropriate for all small rivers. And also some very heavy field conditions here, but my girls were very successful here. An example of the obtained results, you can obtain all velocities, profiles, flows, even the data about the battery, about everything, about the water depth. Here it is. And some mistake errors, if they occurs, you can also see them. And some example of the obtained results. You have many different outputs here, and regarding your request. In most of my cases, I'm using this for the calculation of the potential for the small hydropower plants, and also for some scientific research about the currencies, about the velocities, flow profiles, and so on, so on. Regarding the big depths and also big flows, which you can see here, this is one scalar representation. These are also very precisely and very expensive devices. For example, that one you can see from the left side, and which is always used by boat. Of course, you cannot walk into this very big and very large river. Example about the price here is about the 50,000 of the US dollars. Quite expensive. And you can see this device. For example, also we can use such ADCP, acoustic Doppler velocity profiler, from some bridge. You don't have to have some boat. You can control them by the rope or some remote device. So there are many combinations. Here you can see it, how this looks like. So you're walking from one side of the bridge to another side on the bridge, and here is about the 60,000 euros such device. And also some bigger improvements also requires the larger invest for such device, but this is the top quality and very precise instrument, and only possible instrument for such measurements here. Also, we can try there on very shallow water, but this is not appropriate for such usage here. And also radar ultrasound, you can see radar device, but this is only for the surface velocities. That instrument was obtained from some operation in Japan, the typical program for the karst rivers, for the very small flows, and also where you cannot go simply into these rivers regarding the very harsh relief, very unpleasant conditions for staying in the water, and you can see how such instrument looks like. And there is example of the radar measurements on same water middle, because there are very large velocities here, quite bigger flows, and you don't have to be in the water. You only mount and prepare such instrument, and the measurement is going without your presence in the water. Here you can see this about the 40,000 of the US dollars is the price of that instrument, but you can also measure in all locations where you want to be, but regarding the precision, we can discuss about it. Some engineers say it's quite fine, some of them not, but this is only the question for some discussion. Also, there was some combination of the two different measurement techniques and also measurement devices. You can see now here the electromagnetical and also the radar on the bridge on this fence. You can see the combination, but we have only tried to use on the surface velocity only for the check, not for the velocity and flow profile through the depth. Of course, it was impossible regarding the construction and intention of the measurement techniques here, which is understood. That is only possible for the surface. Ultrasound device, hydrometrical wing on one river in Dalmatia, in Croatia, on the southern part. Also, very beautiful nature here, and we have very, very precise data obtained the result from the hydrometrical wing and also from the ultrasound devices here, and it was very precise on the size of a couple of liters per second, which is very, very quality and very small differences between two measurements. Also, you can see same two devices here. This is an example of the very extreme flow and very big velocity, but you cannot walk into this water, of course. You can use device on the boat or even by using the radar device, because it's quite obvious that you cannot walk here. It will be very, very dangerous. Some night measurements when you have to finish your projects, there is no question where and when you will finish it. You have to finish your task, and you can see how it was very cold. Here, example, like you're on the stage where the rock band is playing or singing here, but very interesting and very exciting experience. And some heavy rain, very big rising of the water, but we have managed all our tasks here. Well, that was everything for me. And of course, I have finished everything I have planned to say. Of course, I can stop my presentation now. And thank you. Please, the floor is yours.
Thank you, sir. That really enhanced our knowledge, and I'd like to ask the participants if they have any kind of questions to you.
Yes, sir. I have one question. All
Yes.
these devices that you mentioned, are this available in India? And how, if they are available, how is India using them?
Yes, they are available for the entire of the world, because we have ordered such devices from California, from the Sontec, and also from one English company. I didn't remember, because we have seller presenter of that company in Croatia. And also, if you want to order something from India, you can directly send them your request into the United States in their company, and they will replay and inform you if there are any sellers in India which are dealing with them. It will be quite cheaper comparing to ordering from the United States of America. And also you can agree some discounts, especially if you are doing this for the scientific or teaching purposes. So all of that instruments are available in each country, also in India. Why not?
So right now, that means these devices are not being used in India.
You don't have something like this in India.
Sorry, sir.
You don't have something like this in India. You are not owner of such instruments, or you're not using such technologies in India.
Okay, okay, okay.
Yes, it's always possible to order, but it's very hard to obtain funding or resources for this. So I'm very familiar. It was also quite hard to me
Okay,
for
okay.
obtaining this. All right, thank you.
Thank you, sir. Thank you.
You're welcome. So there are not any other questions, comments? I will leave my email address. So for all discussions, for our possible collaboration, you're welcome. Thank you.
Thank you, sir, for this session. Now, I would like to welcome Dr. Prabhakar Sharma, an assistant professor at Nalanda University in Bihar, India, to speak and share his knowledge on the impact of aquifer storage and recharge on management of water resources. Over to you, sir.
Thank you. Good afternoon. First of all, I would like to thank Dr. Roy Chaudhary for this opportunity, then Dr. Shahu and other organizer. And I also enjoyed the presentation of Dr. Venkat Raju, and also want to acknowledge Dr. Bjorn Dore. So I will be talking about the role of aquifer storage and recovery and how they are related and useful for water resources management. So maybe I'll share the presentation first. Entire screen. Is it visible? Can you confirm, Satyaprasad?
Yes, sir. Yes, sir.
Okay. Thank you very much. So this basically study is part of one project funded by Australia, in which I think I had Satyaprasad also help part of this duration of the project. So that's very nice. Basically, I will be talking about this aquifer storage and recovery. And we know that it is quite well-known technique for subsurface recharge and increasing the groundwater level. So it is potential for suitability of water resources management as well, especially in terms of groundwater management. This ASR technology can provide a reliable water supply to farmers in drought condition. As we see in this image here, there are a number of benefits in this part. First of all, when we have enough available water, surface water, then we try to inject this into suitable depth. So that can be either shallow aquifer or it can be deep aquifer as well. And this way that aquifer get replaced with the water and recharged with the water, and those water could be available for pumping or for extraction whenever it is needed, whether for irrigation or for other purpose. Of course, there are other challenges like the water quality and other aspect, which I'm going to discuss in this presentation. So how we try to overcome that. First of all, the benefit of overall ASR, it is basically can enhance the water supplies and in different aspect, whether it is emergency storage, that means it provide the emergency supply when the primary source of water is unavailable due to any accidental loss or contamination or any other disaster. But not only that, it also provide and meet the seasonal variability in water demand. That means storage of water during the wet season when there are excess of water, and those can be recovered during the subsequent dry season. As well as not only the temporal benefit, but long-term storage can also be thought about, like a storage during wet year and when distribution facility have a spare capacity, but the recovery during the extended drought years. So on both short-term duration, emergency storage, or even for longer duration, there are multiple aspects of ASR. So overall, it can improve or alter the water quality. So this is the warning basically before we think about injecting the surface water into the subsurface system. So it can provide an inexpensive method for meeting the water quality standard. So one thing is here that they can naturally filter the water if they are of different quality. But if the water quality is different, and then it also there are chances that can contaminate the overall groundwater resources. So that is the risk for any ASR application, which we have to think about. So for doing any aquifer storage, first aspect here is that how do we select the suitable location? So I have listed some of the important point here based on my observation and based on others' work as well. So success of any artificial recharge is contingent upon the identification of appropriate sites, integrated satellite data, geological and geomorphological data, drainage density, or even the land use, land cover mapping. Slope of the land is important as well. The soil type, the rainfall is a very important component because we have to think about the source of water first. Then aquifer thickness is another important aspect for doing this ASR or any other managed aquifer recharge. Majority of the existing studies on ASR site selection do not engage normally the questions of land ownership and willingness of local population to participate in such exercises, which can create hindrance for the selection of appropriate ASR sites. So this technology is not new here, but these aspects are completely getting ignored. Just consider the scientific aspect, which I have just mentioned in previous point. So the site suitable for ASR must not only be based on the local hydrological and hydrometeorological environments, but should also consider the socio-economically feasibility. So this particular presentation is focusing on identification of suitable sites for ASR installation in heterogeneous aquifer of the small place in South Bihar, using the common scientific factor as well as social dynamics. And we try to develop a model framework based on that. So the specific objective of this study was to rate the infiltration, quantity of storage recovery, and transmissibility processes of contamination associated with aquifer storage and recovery. And then to assess the effectiveness of recharge pits. So what we have done here in order to maintain the water quality which is getting injected, we have thought of having a pit which is working for infiltration as well as also doing the filtration. So that we are calling the recharge pit. Then to estimate the user satisfaction, economic benefits, social acceptance, and opportunity for the spread of recharge technology through government scheme and market-based mechanism. So we have also touched upon this part. So this is the study area here in this particular study. and it's located in Bihar, and it's very near to where we are located in Nalanda district. So for our purpose, we have selected 2 small villages and done thorough surveying and other analysis. In this place, it is well known for water stress. Basically, overall, whole South Bihar is in stress due to less rainfall. And due to this, it can adversely affect the winter crop, especially because in the Kharif season, one can manage with the rainfall or for irrigation when there is enough water for enough surface water as well as enough groundwater, for example, because that is usually the major source of irrigation in this area. But when we enter the next crop in winter's crop, then even groundwater is not available for pumping. So basically, there is no water at all for doing any cropping. In this particular location in Bihar, whole state, there are a lot of shallow and deep tube wells because, as I said, it is a flat land, but there are not much surface water supply like a river, canal, and other systems. So mostly dependent on this shallow and deep tube wells. And in these tube wells, farmers are ready, or they are basically investing a lot of money for installation, depending on the depth of borewell. And this is just an estimate. So we can see the image from the same location. I just try to highlight the surface water availability in different month. And this is the point why we have chosen to do the ASR. Because there are huge surface water in this depressed area, which can be utilized. So these are the critical parameter for site selection. We divided into 3 parts: geospatial parameters, physical chemical parameter, as well as the socioeconomic parameter. So very common for geospatial, like rainfall, runoff, surface elevation, land use pattern, water table depth. Then have some of the water quality parameter, like surface and groundwater quality analysis was done. Soil characteristic, aquifer characteristics was also performed here. Then in socioeconomic parameter, we try to gather the information of local knowledge on surface water bodies, aquifer and recharge potential, land holding capacity, willingness to participate, and as well as the infrastructural consideration. Then this is the image of our 2 selected location here. As we can see in this land use and elevation mapping, that this blue color is the depressed area, which we just have seen in the image. So based on this initial estimate, we have selected this black dot for the possible ASR location. So in this left side, we have 3 different depressed area. We call here Ahar. But in other villages, there are slightly bigger sizes of depressed areas. So 4 installation was proposed to be done in the nearby area, because there are huge quantity of surface water availability, which can be used for the ASR for recharge. Some hydrogeological investigation here. The lithologs shows that in one of the villages, there are mostly the bedrock. That means just after 33 meter, it was all like fractured or bedrock. So there is no water, groundwater available. So whatever consolidated porous media was here is very shallow and very thin in this particular village. So they suffered more in the winter crop or in the water availability. So only chance for them is to dig deeper into this bedrock for any borewell. But the success rate, as we know, in fractured aquifer are very minimal for pumping. But in other location, we have a slightly thicker aquifers, even the sand layer or this blue color dot as we see here is thick enough to have the available water as well as for possible recharge, which we have proposed. This water quality analysis, as I said, this is an important criteria for any ASR, and that the water which we are proposed to inject should have enough good quality. We are happy here that our common water quality parameters showed that they are within the limit of FAO, because our goal here is to use these recharge areas, select the recharge area only in the agricultural land. So we did not consider the drinking water standard here for water quality. Only for electrical conductivity for one of the site is slightly higher, but other parameters were under the limit. So we could happily inject it, but still we have used some of the filtration, which I'll come in a moment. Then socioeconomic consideration are this. In this particular study, survey of the household and community mobilization on water needs, flood issues, willingness to participate, and availability of land were conducted before the implementation of this ASR technology. Both extreme drought and flood situation were found, and local knowledge of aquifer and its recharge potential were observed. So these were very, very helpful for us before we go for detailed characterization, detailed investigation, because we wanted to minimize the cost as well. So these information were much more helpful. The interest of farmers for ASR was found to be to secure the irrigation in the time of lower rains and expansion of agriculture in terms of number of crop cycle and crop varieties for commercial purposes. The landowner of flood-prone land were consulted. So flood-prone here, we are just saying that low-lying area. That means those which were temporarily submerged in the monsoon season. So they were the first one to consulted for this, because we wanted this model to be used by the farmer. So here is the design of so-called recharge pit. Although we have found that surface water quality were within the limit, but we had to filter the silt, because we know the surface water brings, especially in the monsoon season, can bring huge amount of silt mixed with the water, and it has to be in the depressed area. So first we try to capture this major silt from this siltation pit, and then injected or passed into the main filtration pit here. And in the filtration pit, first we had a sand layer of about 1 millimeter of sizes, which could immediately filter out the fine particles. But we also wanted to have this activated carbons, because we know that we are using this surface water from agricultural land. So we had, although that particular time it was within the limit of water quality, but nitrate and phosphate could be the major pollutants coming through this. So for precaution, we have used this activated carbon layer of about 10 centimeter. And then in order to facilitate the filtered water easily into the borewell, we have used the gravel and bricks before injecting. So if you see this T joint here, we have used this service pit. That means it was empty, so that we can go and collect the reading from the flow meter, the quantity of water which has been injected, as well as in the emergency situation, the water can be stopped through this gate valve. So we had this empty service pit together with each recharge pit for this experimental purpose. Of course, this may not be necessary when farmers implement this directly. So this is basically overall summary of the recharge pit. The final thing which we have observed here is this conceptual framework in terms of different selection parameters, as well as the different aspect stages of the recharge. That means for geospatial parameter, this water availability can be determined by the rainfall pattern as well as the surface elevation. Similarly, this aquifer storage potential can be based on the groundwater depth. And land use pattern, of course, can help us to understand the land availability. So all this could be identified through this geospatial tool, like GIS-based remote sensing approach. And there are, of course, a number of satellite data available, which was used in this purpose or can be used for other places as well. Then in the field-based assessment are again many, like runoff generation, water quality, both surface and groundwater. Then aquifer characteristics is important to understand, because that determine the overall recharge volume as well as the recharge depth of borewell where we inject the recharge water. The soil characteristic as well. Then socioeconomic parameter, I think are a number of them. Local knowledge help us to initially understand the water availability. Then it is also helpful for aquifer storage potential in because there are a number of old borewells which are present there, but it is very common to have no scientific data for those borewells. So this socio-economic survey helped to procure them. Then land holding capacity, willingness to participate in infrastructural consideration are also needed for understanding or for getting the suitability of the land. So overall, it helps us basically the water availability determine the amount of recharge which can be done at the particular site. And then this aquifer storage potential help us to understand the depth of storage. So that means at which depth this water can be recharged and stored and later recovered. And then land suitability basically help us to design the filtration unit, and filtration unit can be also different depending on the level of the quality of water which is being recharged. Accordingly, it can be done. So if I have to summarize this, then overall, we have used this integrated satellite data, geological and geomorphological data, drainage density, land use, land cover, slope, soil type, rainfall, aquifer thickness data for identifying the ASR sites. The site suitable for an ASR must not only be based on the local hydrological and hydrometeorological environment, which is commonly being done so far at most of the ASR design, but it should also be socio-economically feasible. So based on these findings, we proposed this entrepreneurial farmer-led model. And the critical element of this model could be a multidisciplinary approach to site selection, in which scientific assessment can be integrated with socioeconomic insights, system may be initially adopted for entrepreneurial farmers who agree to invest and share the benefits. So this is our primary target for selecting the sites, and we have observed after this has happened 1 year ago. Now many other farmers are also willing to adopt and willing to invest their own for building this ASR. So we are still helping in co-designing the recharge pit using the locally available material and ease of maintenance. So that's all from my side. These are some of the references which I've used in this presentation. Thank you very much. I will be happy if you have any question.
Hello.
Yes.
Yeah. So myself Uday Mondal, and it is very good. First, my compliments to you that it's by telling and by doing in field, it's a very difficult job, but you have done that job. I have some curiosity actually, not rather question. So once you have told that for the agricultural purpose, we are actually researching.
Yes.
But because we don't have the fixed boundary, like surface water body, we have a clean boundary, we are putting water, we are taking water like this. It is very fine. But for the groundwater, there is a huge chances of mixing the water with the other. And if there is, even we don't know that water extension in how much actually. So is it using for maybe other location that water is moving? Is it not? So,
Yes.
but my concern is that considering agriculture purpose, I hope it will be maybe problematic for the other location, as because we don't have the exactly boundary of the groundwater.
Yeah, I completely agree actually. So we have also had the similar concern. So in order to consider that, we had used this activated carbon. So first of all, of course, we had thoroughly checked the surrounding borewell water as well as surface water. So both groundwater as well as surface water survey were done. And then in order to have the safety, and it was at least more than almost like 1 kilometer away from the any drinking water source. So that we have made sure. In addition, we have put this, included this activated carbons, and we are studying in the lab. Activated carbon is very suitable for reducing the common pollutants coming from this area at least, or any other. So at least it worked very well for phosphate and nitrate. That I'm suggesting to use for any recharge. So I totally agree that we have no common bond, no defined boundary. We cannot stop, especially when you have a gradient, very strong gradient of groundwater towards the inhabitant or towards the village. Then it is more challenging, more difficult. So, and that was probably the case here where I worked. So we had taken that care, and now we are thoroughly after like 1 year of recharge, we are still measuring those surrounding borewells water quality. So we are creating so it's still an ongoing work. So we are trying to understand how much impact they are having for the water, groundwater
Okay,
quality.
thank you.
Thank you very much.
Sir, I have a small question, sir. May I ask?
Yeah.
Sir, many of the groundwater recharge processes, they use a charcoal for filter media, many places. Now we are finding that many places charcoal is also not available. If it is available, very costly, or many times it is not available also. So is there any alternative material for other than this charcoal, sir?
Yes. I think you are totally right. we have encouraged here to use the locally available material. So that was one of our priority. Of course, you know that when we are doing anything for experimental scale, then we don't want to invest our time in that part. But charcoal can be used, or this activated charcoal, which I mentioned here, is not very expensive, and it was also locally available. But one can use any other media, like right now I'm working a lot on biochar, for example. So biochar is also a good filtration medium. So any filtration medium can be used depending on the pollutant. So that is why it is always important to do the proper survey of water quality of both groundwater and surface. For accordingly, we can opt for the recharge and this filtration medium together with the recharge bit.
There are
Any
some
locally.
materials are in the market like synthetic fiber material, other things. Can we use them?
Why not? I mean, as long as we have a control over our own recharge pit, which is artificially built, we cannot control when the water went inside the groundwater, but we can control very well when it is in the recharge pit. So certainly you are free to test and use that part also. Synthetic media, there are many. So whichever is economical and easily available over there.
Because we heard that charcoal is very much good, effective in biological pollutant control, like some bacteria.
Yes, they're already.
I don't know whether this synthetic material will also help in that particular way.
I don't know that which synthetic material we are talking, because each medium can behave differently. I am especially working on number of filtration medium. So unless I tested particular medium, we cannot comment on that. Otherwise, so it's better to test and know which filtration medium we are using.
Thank you very much, sir.
Sure. Any other comment, question? If not, then you can go ahead, Bhumika.
Thank you, sir. This session was brainstorming indeed. Now, I'd like to extend a warm welcome to Dr. Karthikeyan Lanka, an assistant professor at the Indian Institute of Technology, Bombay, the Center of Studies in Resource Engineering, speaking and imparting his expertise on soil moisture estimation using microwave remote sensing in India. Over to you, sir.
Am I audible?
Yes, sir, you are.
Okay. Yeah. Let me share my screen. Just a second. Is the screen visible?
Yes, sir.
Okay, thank you very much. And good afternoon, everybody. First of all, thank you very much for inviting me for this workshop. My name is Karthikeyan. I'm working as an assistant professor in CSRE, IIT Bombay. I'm basically a hydrologist with inclination to work in remote sensing. So I have my current interests related to microwave remote sensing of soil moisture, and I also work on agricultural droughts and also in land atmosphere interactions. So I thought I'll give you a quick overview about this particular area of soil moisture estimation using microwave remote sensing. Since I still observe that this area is still emerging, especially in India, and it has a lot of potential. So before get into details, so I thought I'll just quickly present a basic idea about remote sensing. So whenever we start with talking about remote sensing, we first explain about electromagnetic wave spectrum. So wherein our sun emits radiations in various wavelengths or frequencies. So visible spectrum is one such spectrum in which we are able to visualize things, or we are able to see the things with our eyes. Apart from that, we also have infrared spectrum, UV spectrum, or even the microwave spectrum. So specifically, we are interested in studying about the microwave spectrum. So if we try to understand what is microwave spectrum and why microwave spectrum is so important in the context of soil moisture, I'll try to explain that aspect shortly. So when we are talking about microwaves, many of our homes, we have these microwave ovens. So we may wonder, like, are these the same microwave radiations that we are talking about? A simple answer is yes. Both the microwave ovens or microwave satellites, all of these emit or capture the microwave or the electromagnetic radiations in microwave spectrum. Okay, so now it's just that they will be operating at different frequencies or wavelengths. So see here, as I show you, this is the range in which the microwave spectrum is, and which is having different frequencies or wavelengths. So based upon the frequencies or wavelengths, they will be used for different purposes. So if you look at the other applications, the microwave remote sensing or microwave satellites are used for telecommunication purpose, or even navigation, etc. So in many of our houses, we also have this dish connection for the television. So that operates in microwave spectrum. Okay, so now if we look at the type of sensors that are generally available, so we have something called as a radar, and we have something called as a radiometer. Okay, so these are the two different types of sensors with which we try to do remote sensing of soil moisture. So these radars generally operate, or they are generally called as active microwave sensors, and whereas radiometers are generally called as a passive microwave sensors. Okay, so I will describe what is the difference. So basically, the purpose of this talk is to give you a big picture overview of how we do this remote sensing of soil moisture. So I'm presuming many of you in this talk would be aware of what is soil moisture, but anyway, I will give a brief overview about that as well. So now, as I said, we have two types of sensors, radars and radiometers. So they are classified as passive remote sensing systems and active remote sensing systems. Okay, so when we are looking at the passive remote sensing system, okay, so we are essentially dealing with satellites which would capture the naturally emitted radiations from the Earth's surface. Okay, So what happens is any body which is having a temperature of greater than 0 Kelvin can emit radiations. Okay, so for example, even our human bodies, they will keep emitting radiations. Okay, so they are emitting radiations, which is why we, our eyes are able to perceive other human beings, because the other human beings or any other objects, they are able to emit radiations. Okay, in the same way, these radiations would be emitted not just in the visible spectrum, but also in other portions of the electromagnetic spectrum. Okay, like UV or infrared or microwave, etc. Okay, so now each of these signals, whatever would be emitted by the Earth's surface, will be having this unique information about the material from which these radiations are being emitted. Okay, so suppose again, if we take human beings are emitting radiations in visible spectrum. So they, if you're looking at them only concerned with the visible spectrum, we are trying to find out, like, what would be the color of the skin. Okay, so that actually information is being transmitted through these radiations that are emitted from the human body in the visible spectrum. So similarly, these signals would be emitted in other parts of the spectrum, and we are interested in this microwave domain. Okay, the signals that are being emitted in the microwave domain. So those signals would be captured by a radiometer. Okay, so this would be a radiometer. Now, if you take the active remote sensing systems, okay, so this satellite itself will have a transmitter. Okay, so it would transmit its own signal towards the Earth's surface, and it would capture the scattered radiation which is emitted towards the satellite. Okay, so again, whatever is the scattered radiation would be carrying the signal about the target material. Okay, so this is how the two different forms of sensing systems would be working. Okay, so here, in the case of passive sensing system, we are talking about the emitted radiations, whereas in the case of active sensing systems, we are talking about the scattered radiations. Okay, so the type of methods that we use to convert this information, that satellite is measuring into the information about the target would be completely changing. Okay, so now how exactly, if you slightly go deeper into how these radiations are interacting at Earth's surface. Now, whatever is the radiations that are emitted from the sun, they travel through the solar system and they enter the Earth's atmosphere. They interact with the gases and dust particles, etc., in the Earth's atmosphere, and finally they will reach the Earth's surface. Okay, so the Earth's surface can have different types of landforms. Okay, there can be water bodies, there can be trees, there can be agricultural lands, there can be just barren soils, okay, etc. Now, what happens is, whenever this radiation interacts with the surface, some of these radiations will be absorbed, some of these radiation would be transmitted, or some of these radiation would be reflected. Okay, so this is where all the magic happens. Okay, so the manner in which this incident radiation is being split into these three components would actually affect, or would be decided by the properties of the material. Okay, so now when we are talking about the active sensing systems, okay, so we are essentially talking about these reflected radiations, okay, which would be carrying the necessary signals. Now, in the case of the passive sensing system, what happens is, whatever is the energy that is being absorbed by the surface, okay, would be re-emitted back to the atmosphere. Okay, so this emitted radiation is what is being captured. Okay, so this is how the two sensing systems would be behaving, and this is how the reflected energy would be different from whatever is being emitted by a body. Okay, So the reflected energy would be captured by an active sensing system, that is a radar, and an emitted signal would be captured by a radiometer. Okay, so that's a quick background related to remote sensing. Now coming to the soil moisture, okay, I could see some very relevant talks that are happening prior to mine. Okay, so soil moisture is where we are talking about the unsaturated unsaturated soils. Okay, so where we are talking about a soil matrix that consists of soil particles, water, and air. Okay, so basically the soil particles will have voids, and these voids will be either filled with air or water. Now we define soil moisture as a ratio between the volume of water that's present in the soil, in this particular soil matrix, and the total volume of the soil. Okay, so basically if you look at it closely, this particular ratio has a very strict limits. Okay, so either the soil moisture can be zero, that means theoretically it can be zero, that means there is absolutely no water present in the soil matrix. Okay, there is just the air voids, or otherwise it can go as high as the porosity. That means all the voids present in the soil are just filled with water. Okay, so there are also other components which would affect the soil moisture, like the presence of organic matter, the roots and all. But majorly when we are talking about soil moisture, this is how we would be splitting the composition. Okay, soil containing soil particles, water, and air. And we try to express the soil moisture as in the form of weight units or volumetric units or depth units. Okay, now this is where things get trickier, because when I'm talking about a range, okay, I'm talking about a range of anywhere between, let us say 0.05 to 0.6 meter cube per meter cube. So this will be the typical range of soil moisture for most of these soils. Okay, so now this looks very small. Suppose if you take about aquifer recharge, or the rainfall that occurs, or the stream flows that occur, the magnitude of changes that would occur would be significant. But whereas in the case of soil moisture, no matter what you do, okay, the range is always restricted in such a tight numbers. Okay, so now, but still there is a very increased importance of soil moisture in the last 2 to 4 decades. So because what is happening is it's present exactly at this interface between atmosphere and the land. So therefore what happens, it is able to regulate how much of regulate how the precipitation is being split into components of the seepage or the evaporation or the runoff. Okay, so and also the whatever is the amount of evaporation that is occurring from the soil would be subsequently contributing to the precipitation. Okay, so we call this as a concept of recycled precipitation. But in all of this, the soil moisture is playing a very big role. So apart from that, if you look at the applications, soil moisture is very important for in the hydrological models or even in the weather prediction. Okay, and also it has very important agricultural applications, like in terms of crop yield estimation, and also irrigation water management. Okay, so this is the reason why there is a lot of attention towards estimation of soil moisture these days. Okay, now if you look at, again, coming back to the rationale of how we can use remote sensing to talk about soil moisture. So here generally, if you talk about these microwave measurements, this can be either radar or radiometer. Okay, so now these as I said, the radar estimates the emitted radiations in the form of something called as brightness temperatures. Okay, whereas a radiometer estimates the the backscattered radiations. Okay, now these two are the measurements made by the satellite sensor. And now how do we infer about the soil moisture? So generally what happens is, in the microwave spectrum, suppose if we are concerned with at lower frequencies of microwave spectrum, okay, so the whatever are the measurements made by the sensors would be sensitive to the dielectric properties of the soil. Okay, so these soil dielectric properties, because basically these are the electrical properties of the soil. Okay, they talk about the conductivity nature of any soil medium. Okay, so now this soil dielectric properties in turn are very much influenced by the amount of water that is present in the soil. Okay, so therefore, if we are able to estimate the soil dielectric properties based on these either radar or radiometer, subsequently we can infer about the soil moisture content. Okay, so this is generally the rationale of how we use these microwave sensors to infer about the soil moisture. Okay, so when I'm talking about this soil dielectric properties, okay, the dielectric properties of dielectric constant of soil lies anywhere between 4 to 5, whereas for water, it's pretty high, it ranges anywhere around 80. So because of this big contrast in the dielectric constants of water and soil, okay, whenever there is a small change in the water content of soil, the entire soil matrix's dielectric constant would be getting altered. Okay, you can see that from this particular graph. Okay, you can see on x-axis we have the moisture content, and on the y-axis we can see the dielectric constant. Okay, you can see that how with a small change in the soil moisture content is resulting in an exponential change in the dielectric constant. So therefore, what happened is, by the way, we have two components of a dielectric constant. We have the real part and we have the imaginary part. Okay, so we are for the sake of time, I just want to mention that we will be only concentrating on the real part of the dielectric constant. Okay, now as you can see, this is for different frequencies of microwave spectrum: 18 gigahertz, 12 gigahertz, 6 gigahertz, or 4 gigahertz, 1.4 gigahertz. Okay, as the frequency of this these radiometers is reducing, okay, you can see that it's more and more sensitive to the changes in the soil moisture. So that's why, for the sake of soil moisture measurements, we try to focus on the lower frequencies. Okay, the lowest the lowest possible frequencies for soil moisture monitoring. Okay, now I'll try to provide some overview about what are the satellite missions that are available. Okay, so one of the first dedicated satellite mission is launched by ESA, which is a European Space Agency, which is the Soil Moisture Ocean Salinity Mission. Okay, so this was launched in 2009, and it started to provide data from 2010 onwards globally, and which is free of cost. Okay, so it's providing currently soil moisture in the range of 35 to 50 kilometers with a three-day revisit time. Okay, so this also has an L-band radiometer, and more recent satellite is basically soil moisture active passive sensor, which is SMAP. This was launched by NASA in 2015, and this is quite accurate in terms of providing soil moisture across the globe. So we have some soil moisture products which are at 36 kilometers, and we also have a 9-kilometer soil moisture product generated by the SMAP mission. Okay, so this is how typically the SMAP soil moisture soil map would look across the globe. So you can see I have highlighted two regions over India. You can see the Rajasthan, which is having a very low soil moisture. So by the way, this was captured around April 22nd, 2015. And so you can see the dry regions being captured, and also you can see the wet areas of northeast being picked quite nicely by the sensor. Okay. So now the one downside with these passive microwave sensors is basically their poor resolution. You can see that we are talking about one measurement of soil moisture at every 36 kilometers or 9 kilometers. Okay, so this is this can be addressed in one way through active microwave sensors. Okay, because in the case of active microwave sensors, they transmit their own energy and they capture the scattered radiations back. So they will be having a much stronger signal to have better resolution. Okay, so these scattered radiations are called as the backscatter coefficient. Okay, so these backscatter coefficient, as I said earlier, are dependent on the dielectric properties, and again, the dielectric properties can be used in turn to estimate the soil moisture. Okay, now in case if there is some amount of vegetation present on the top of the soil, okay, be it as a crop or through as a forested area, okay, there would be some amount of signals that are coming even from the vegetation. Okay, by the way, this applies for both the forms of remote sensing, passive as well as active sensors. Okay, so we need to even account for such changes that are occurring due to vegetation to extract only the signals that are contributed by the soil. Okay, now coming to the sensors. Okay, so we have one homegrown sensor, which is ISRO's RESAT mission. The RESAT 2 was launched in 2009 and RESAT 1 was launched in 2012. And then there is also a very exciting satellite mission that's coming up, which is through a joint collaboration between NASA and ISRO. So this is called as NISAR. So this is planned to be launched in 2023. Okay, so among several other applications, soil moisture monitoring and vegetation monitoring are two key science objectives of this particular mission. Okay, so this has an L-band synthetic aperture radar, which is equipped. Okay, and coming to some of the finer or high-level applications, so we have been trying to work on improving the resolution of soil moisture through different techniques. Okay, so one of such technique is to use some machine learning methods. Okay, now these days machine learning has become quite popular. So we try to exploit the strength of this machine learning to see if we can improve the spatial resolution of soil moisture, and we developed a workflow on that. So we were able to generate soil moisture maps at a daily resolution at a spatial resolution of 1 kilometer. Okay, so this methodology was tested over in the United States, and currently we are also trying to develop this method for a similar method for Indian conditions, which wherein we wanted to incorporate a lot of in situ sensors and also drone based soil moisture measurements, and eventually put them in machine learning framework to get much higher resolution soil moisture that would be subsequently used for irrigation water management. So this particular idea is in pipeline, and we are actively submitting proposals and to achieve this particular goal. Okay, so that would conclude my talk, and thank you very much. I'll be happy to take questions. Thank you. Am I audible?
Yes, sir, you are.
there are no more questions, then yeah, I'll leave it up to the organizers.
Thank you, sir. It was really a great session. Now, I would like to extend a warm welcome to Dr. Uday Mandal, scientist at Hydrology and Engineering Division, ICAR, that is Indian Institute of Soil and Water Conservation, Dehradun, India. I'd like to wish a hearty greeting, speaking and sharing his knowledge on the use of a spatial scientific method to identify groundwater potential zones for agricultural use.
Hello, am I audible? Am I audible?
Yes, sir, you
Yeah,
are.
thank you, Bhumika. And so, first of all, I would like to convey my sincere thanks to the organizer, Dr. Rai Chaudhary, Dr. Shahu, for inviting me on this occasion. And I also like to convey my sincere thanks to my honorable director and head of the division, allowing me for this participation. So, without wasting time, directly I am going to the presentation mode, and during that time we will discuss more. So, I'm sharing my slide. Uh, so I'm getting this. So my slide is visible.
Yes, sir, it is.
So view full screen mode, and it is in presentation mode.
Yeah, yeah. Go ahead.
Yes.
So good afternoon, everyone. And so today's topic was that geospatial technology. That webinar was on the geospatial technology and water resource management. So I have chosen one topic like identification of groundwater potential zone using geospatial technology and its application towards the agriculture. Okay, so in very beginning, I'm showing a classical example of application of remote sensing and GIS or geospatial technology application. So it is developed by Roden et al. And he published 2009. And he has conducted the research on the satellite-based how the water, groundwater withdrawal or percentage of groundwater withdrawal of a recharge. So for the India, and it is showing in this figure, three estate was alarming. Okay, so based on what? Based on the NASA GRACE satellite data with combination with the simulated soil water variation from a data integrating hydrological modeling system, they have found the groundwater is being depleted by 4 plus minus 1 centimeter per year. So it's a 2002 to 2008 data they have used, satellite data. Okay, and this is a very classical example, definitely. And today that I am also going in very detail for a particular small area of India as a case study to show you how the remote sensing and GIS together with some technique like ASP or multi-criteria decision making, we can go for a groundwater resource assessment. Normally in surface water, it is very easy to assess by using satellite data. But for the groundwater, and as we know that groundwater is the most important water resource for India, because the FAO report is saying that 87% of the irrigation is happening from the groundwater resource itself. And if we see the data a little bit, that it was 1951, it was irrigation potential was irrigation was 14%. Now in 1995, it is 56%. However, the World Bank report says it is 35%. Even we are assuming it is a 35%. So within that 35% is covering 86% from the groundwater only, and which we can't visualize even, and we can't assess easily. Okay, so through this lecture, I will try to convey some message that indirect way with the help of satellite imagery, how we can going to assess or manage the groundwater resource. So integration of remote sensing GIS and ASP, that is analytical hierarchical process or multi-criteria decision making technique, together has the potential for sustainable water resource management. So I am audible to all. Am I audible clearly? My voice is.
Yeah.
So just for your example, many people are doing research on the same aspect. Actually, it is not the new things, but the application, how we can implement actually in the ground using the technology. Okay, so various researchers already they have published their research paper based on various layer they have used, which is combination of from the satellite imagery as well as from the conventional map available. So objective is that today's lecture to identify the groundwater potential zone. Okay, so for that I have chosen a study area. All might be knowing that Suvarnadaka River Basin, which is situated in the eastern India, that Odisha, West Bengal, and part of Jharkhand. And the very lower part in this figure, you can see it's a small part we have chosen from that river basin as our study area to realize the practical application of that technology. Okay, and this area is nearly almost plain land. So 0 to 2% slope is around 46% of that area, and 2 to 5% under this it is 35%. So it is near about 80% slope is under the 8% slope, and this figure is showing is a schematic diagram where we can say this. As I already told you, this is a combination of satellite data as well as your conventional map available or layer available with us. So in the conventional maps, that soil map, surface geology, geomorphology, and hydrogeology map is available with a different agency. And next is the surface water modeling. One of the speaker already told that hydrological model is the backbone for assessing the water resource. So without lifting that hydrological model, even that Roden et al. Developed the map for India withdrawal, percentage of withdrawal. That is also a combination of satellite imagery as well as that simulated hydrological model outcome. Okay, so using that SWOT model, that soil and water assessment tool, it's a hydrological model. So using this digital elevation model, land use, land cover map, it's a product, both are the product of the satellite imagery and slope, and then weather parameter. Okay, so from that we will get the recharge rate, and I will little elaborate how we are getting the recharge rate for from the SWOT model and how we are utilizing in the groundwater potential zone estimation or prediction. Another is a Google Earth, from where we have taken the surface water body. So normal, small. If it is a big water body or it is a river or stream, directly we can get from the satellite imagery. But if it is a like pond in eastern zone, if you see in West Bengal, in Odisha, and Bihar also, so there is a ample number of small we can water body. Normally we used to say it's a pond. Okay, so that information collection and having a major role on the groundwater potential zone estimation or prediction. So we have extracted the information from the Google Earth imagery itself, which is also product of the remote sensing. And there is a dam, then slope, drainage density, lineament density, some secondary layer actually, which is derived from the satellite imagery. And another was the land use land cover classification and NDVI, which is also product of the satellite. So with the combination of that and process and using that analytical hierarchy process ASP and weighted sum method, we can estimate the groundwater potential zone. So indexing, this is indexing method and weight sum approach, we will get a groundwater potential zone map. And after that, we need to analyze the sensitivity of the parameter, because in this study I have used 12 parameters. Okay, then validation. Of course, if you are putting some map and you are overlapping something and weighted sum you are doing, so you will get some output. But that does not mean you are getting everything. So sometimes people used to say that without down-truthing remote sensing is non-sensing. So it's a product of remote sensing as well as the conventional map available. So definitely our responsibility to validate it. Unless until we are validating it, it is difficult to implement. Okay. So these are the mathematical expression. So groundwater potential index, we will estimate, we'll find out the value using this equation. And finally, we will use the ASP, that is the analytical hierarchical process. And there we have to calculate the eigenvector, eigenmatrix, eigenvalue. And finally, we have to estimate the consistency ratio. If it is less than 0.1, then only our matrix. I will show you one example as example for matrix, how we will create the matrix, how we are going to integrate the different layer. Okay. Then if it is less than 1, then we will go forward. Otherwise, we have to check the matrix and we have to give the different value. And then sensitivity analysis, sensitivity, because we are using maybe n number of parameters. So this concept was that if we omit one parameter and if we have the using the all parameter outcome, so what is the changes from one zone to another zone? So this equation, I represent the parameter number and J represent types of zone. So in this zone, if we considering it's a 4 groundwater potential zone, like good, very good, poor, and moderately good. So J will be the 4 maximum. So how it is changing if we change one parameter? Okay. Then parameter I have used in this study, and you may change according to your availability of data and your local condition actually. It's not like that you have to use. I have shown you one table that many researchers are using different types of parameter. So whatever availability and at the same time the importance of that parameter for that particular area and condition also. So here I have used 12 parameter like land use, soil, geomorphology, surface geology. So geomorphology, surface geology, and hydrogeology map we have taken from the state government, that is groundwater survey and institution department. Soil map from the NBSS UP, and land use land cover we have classified the image Landsats ETM plus 7 image. Okay. Then drainage density, recharge rate. Recharge rate we have estimated from a hydrological model, and I will come how I got. Then rainfall, it's a block-wise data available for that particular area. Then slope, it's a product of the DM data. Surface water body, as I told you already, that it is extraction from the Google Earth. Then lineament density and normalized vegetation, different vegetation index. So these are the mathematical expression for calculating some parameter. And recharge rate if you know that hydrological model, one of the most important and very popular model for hydrological modeling, that is SAIARD model. So from that model, that recharge rate for a day we can estimate. And in each and every HI, because hydrology soil SWOT model is working on a HRU basis, that is hydrological response unit, which is a smaller unit of the subwatershed. So here I have shown you an example tree of subwatershed. Okay, so but within this watershed there is many HRU. That HRU also depends on the land use, soil, and slope properties. So this is example from where how we can convert actually. If it is a watershed and you see there is a 5 number of HRU. So how we will get, now using this equation, we can convert that sub HRU recharge rate to a subwatershed recharge rate. Okay. And this is one example. If I have told you this is I have used the 12 layer, so this is 12 layer. So it's a comparison matrix, pairwise comparison. Means if you see the land use and land use, there is no change. But if we see this, so land use is 7 times, uh, 7 by 6 times important than the soil. So if you go through the Shetty 1980s concept paper, that ASP and many other research are available, so you will understand actually. So similar way, this is the features. And if we talk about the sub features, that means within the land use map, I have classified in 9 land use, different sub features. So similar way you have to create, because you know that settlement will not give you the good potential for groundwater storage, groundwater potential zone, but the agriculture or forest will give you much more chances of or occurrence of groundwater potential. So within the layer or features, there is a sub feature. So you have to generate each and every layer sub features matrix. Okay. So like this table will tell you everything. So if, for example, land use, land cover is our features, and you know from this matrix we have calculated the normalized weight. It is not simply summing and divided by first one, the layer value divided by total. It's not like that. It's a ASP matrix. We have used this technology. Okay. And this value came here actually. And within the features, there is a sub features, as I told you already. And you see the percentage area, how much it is covering, and what is the prospect, each and every, and rank. And at the same time, it is a rank only. But like features, you have to create a sub-features matrix, each and every layer, and you will get this value, normalized value, and this will multiply with this will multiply with this for that particular features. Okay. And as I told you, so it's an example. So slope, for slope, this much of area, this much of, if you see for the area of slope, that is 0.2%, this is 45% area and above, and it's a high impact because slope is less means the opportunity time of the water standing on the surface is more. That means opportunity of the infiltration will be high. So that means there is a more chances of groundwater potential. Okay. Similarly, drainage density, if you see, there is a value of 0 to 12. And if you see that the value is 0 to 1 means less drainage density. Less drainage density means the number of drainage is less with a particular area. What does it mean? If it is less means, so there is a more chances of water for the surface flow. That means there is a chances of more infiltration if it is gone immediately to the to the to the drainage or river. So that means it is surface flow, it is going outside of the system. So it is a less time for the infiltration. So that means if your intensity, drainage density is more, that means there is a poor chances. Okay. So similar way, every layer having importance, and within that layer also there is some difference, significant level is there. Accordingly, we have to assign we have to prepare the matrix and we have to estimate that value. So these are the example as I told you. So I am not taking too much time to explaining each and everything. Okay. This all layer you can see. You see this is a surface water boundary, which is actually difficult task to extract from a Google Earth, but we did actually, and it having a most later on we will see the when we go for sensitivity analysis, then the surface water and NDVI is the most important parameter. Then after getting that all, and if we do the overlay, definitely it is in ArcGIS environment that weighted sum. We have used the technology because we have defined. So layer, we have converted the layer into each and individual layer with this value actually. So every layer, sub-layer having this value we have assigned as per the land use. So for example, agriculture and cropland, we have given the value. And at the same time, we have multiplied this. So it will multiply each and every layer. That will be the actual weighted value for a particular layer. And if we sum that all, we will get a final output like this. So this is groundwater potential zone. And if you see this map, so, and this map is showing there, you can see this is some observation oil are there, that is oil ID. Okay. So red color is the very good potential and green is good. So you see with the very good, there is a good, then moderate and poor. And our observation oil is lying almost maximum in the very good to good zone. So we will see the statistics. So this is the accuracy statistics, or you can say it's a validation actually, that we have taken the data, ground data from the lift irrigation corporation department from the Balasar and Odisha. So you see, if it is a moderate, then we have given a partial agreement. If it is good quality of potential, we are giving its a grade. So with this, there is a 6 number of oil, it's showing the partially agreed. Okay. And 5 number is disagreed and 24 is agreed. So we have calculated the accuracy is 85%. And I was talking about the sensitivity analysis. So using this equation, I already explained this equation. So we can see here the percentage of area changing if we omit one layer. Okay. So, and I will say that in conclusion, exactly the which is more sensitivity, but it is not the totally remote sensing GIS application. But to show you one example, as an example, it's a hydrological model framework, which is required the remote sensing and GIS data as well as the conventional. So from there, we are getting the Richard's rate value, which is using here. And another is it is an optimization framework. If we demand more water extraction, it is required. Okay, from this, and we have a quality map, groundwater quality map, that quality index map, from where we can assess that spatial distribution of a good groundwater quality for agricultural purpose as well as the drinking purpose. So if we superimpose this, this is actually quantity aspect, this is quality aspect. So if we overlay both, we can find out the most suitable location for pumping if we require, because it's a big study actually. Just I am showing for example. So if you having optimization model and you are demanding for the agriculture this much of water is required, and you have the potential map, you have the quality map. Okay. So we using this 3 map, you can go for the exploration of the new groundwater extraction location. So we will target the most suitable area, that is a very good, then good location. So there will be more, why we will go for, because there will be more less chances of failure. So it will save the economy, definitely it will save the national economy also, because it's a product of the remote sensing, but we have validated from the ground data. So that's why with more confidently I can say, if you follow, if you, that map can be a guide before going to field where I should go for further exploration for extracting the groundwater to meet out the agriculture demand or domestic demand. Okay. So This is in summary, we have classified in 4 category. I have told you, and maximum area it is coming under good category, and then good. So validation is 85%, and the sensitivity NDVI, surface geology and soil and layer are the most sensitive parameter. And groundwater potential zone map can be used as a tool for identification of possible location for construction of new tube wells, may reduce the economic loss from failure. And integration of remote sensing, GIS, and ASP or multi-criteria decision-making technique together as act as a handy tool for effective water resource management. So I already convey my acknowledge to the organizer and my director and my head of the division. So thank you. So it is from my side, it's ending. So how can I stop this sharing? I have stopped
Sir,
the
it is
sharing.
already, yes,
It is
sir, it's
unshared.
already stopped.
Okay, thank
Yes,
you.
sir.
So any question or any discussion, I am happy to reply, or if not possible, then I will communicate through mail. So if there is no question, then I may over. So mic over to the organizer. Thank you. Yeah, Bhumika.
Yes, sir.
If there is no
Thank you
question,
so
then
much.
yeah.
I don't think if the audience have any kind of queries, if you can drop your mail in the chat box so they can reach you out if they have any queries. It was a great session indeed. Now, I'd like to heartily welcome Dr. Pulkesh Das, the Senior Project Associate, Sustainable Landscape and Restoration, World Resources Institute, New Delhi, India. I want to extend a warm hello, speaking and imparting his expertise on the automatic near real-time flood monitoring and susceptibility assessment. Over to you, sir.
Thank you. Thank you to the organizer for inviting me to this event, and I congratulate all the organizer and convener. So let me share my screen. I hope this is visible to all of you.
Yeah.
Yes,
Thank
sir,
you.
it is visible.
So this is one of our case study. We three were engaged with this work. I and two of my friends, Sujoy Modi and Jayaprakash. They are from IIT Kharagpur. So we did this small work in Assam, and the topic was near real-time automated flood mapping and hazard assessment. So you might be watching news or getting news from different sources that the state of Assam is experiencing like recurring flood events in every year, and this kind of your extreme weather events or flood events are causing your affecting the socioeconomic condition of millions of people, causing human and wildlife loss, and then displacing permanently or temporarily, and it is also causing food scarcity or damaging ecosystem or infrastructures. So the intensity of flood mostly depends on the kind of geography and the impact on the socioeconomy or the wildlife mostly depends on the flood preparedness or the mitigation action plans. So it is very necessary to map the flood events at a real time, and if someone is or if we can map the flood events at a periodic interval and at a long-term basis, we will be able to develop your your appropriate policies of preparedness to mitigate such events. So remote sensing is a powerful tool to map such events or the water inundation and also assess the flood hazard, especially if it is happening in remote areas. So we all know that the optical remote sensing has certain limitations. It can be it can only map the water your spread in daylight, and under cloudy condition it cannot map the water extent. And mostly if you see like this kind of flood event mostly occur in monsoon. So we have a like your limited satellite data availability, like optical data availability in this kind of a period to map the water inundation. So this is one example from your state of Assam. You can see this is a cloud-free image in pre-monsoon, but if you see the monsoon image, you'll find like a lot of clouds are there, and it is not possible to map the actual your water inundation or water extent during the monsoon period. So on the right-hand side, there is one your example of microwave satellite data. One of our previous speaker, gave a very your detailed your information about the microwave remote sensing. So, so you can see like under cloudy condition, you can also get a your clear picture of a particular area. So as you know, like microwave sensor, sometimes it used to be an active sensor with when it has its own your source of your energy, and it operates at a much higher wavelength that allows it to penetrate the clouds. And if we like analyze the backscatter values from your different land surface feature, one can easily demarcate the surface water from the other land cover features. However, it has some limitation if someone is working on the urban areas, like due to this your oblique angle of sensor and your scattering from the artificial structure, there could be some error in water inundation layer. So the major concern was data unavailability. So earlier the micro data was not available publicly, or sometimes the real time or near real time data was unavailable. But this Sentinel-1 data provided by ESA providing very high resolution microwave data, which is having UV and pH or polarization bands, and it can map one area in every 6 days. So, but there are a lot of studies which have been which have used this Sentinel-1 and other microwave satellite data in water inundation mapping and flood assessment. So this is a simple methodology we applied. We took the your Sentinel-1 SAR data for 3 years, and then we did some applied some your pre-processing your steps, and then based on the backscatter values, we applied this Otsu's algorithm to identify the water spread areas. And then for verification, we used the optical data, the Sentinel-2 optical data we used, where we applied the NDWI. This is basically a spectral index to map the surface water spread, and we tried to verify the water spread area identified by the satellite your microwave data. And then we took multiple year data and the land use land cover map to assess the flood hazard. So on the left hand side, you can see this is the histogram generated using the Otsu's algorithm over the VV band. And on the right hand side, we have overlaid the identified water inundation on optical data. So, but like in although there could be like your clouds in optical data, but in few regions one can get some cloud-free scenes. So those cloud-free scenes areas can be used such kind of your validation. And on the left hand side, we have some your field photographs, and on the right hand side you have the water inundation your map identified in different years, and those we overlaid on the land use land cover map to identify the different land cover features which is under flooding condition. And this is the area statistics where we identified the different land cover features which experience the flood inundation. So the basic purpose of the study was to create a automated platform. So we employed this entire data processing in the Google Earth Engine platform, and this platform can quickly analyze the data. Like within couple of minutes, it can create a water inundation map. And if you see, like as of today, we have very recent image available. Like we have the latest image available for 28th June. So this particular your Sentinel-1 data is available at near real time. One can use this data for water inundation mapping at a frequent interval at a near real time. And if someone is executing in a Google Earth Engine platform, this can be made a like your real-time flood mapping, which can help the decision makers in disaster management or relief-related activities. Yeah. So on the left-hand side, you can see this is the latest map we have created. This is the flood inundation showing for the month of June 2022, and this is one of our field photographs. Thank you. If anyone have any question, you can ask or and then. I think there is no question. Then go back to the organizer.
Thank you, sir. That was a good session indeed. And even the good times tend to end, and so is our meet today. And hereby, I'd like to invite Ms. Bulu Bashak, the faculty of IITST, as well as the joint coordinator of this event, to wind up this session and deliver the vote of thanks. Over to you, ma'am.
Thank you, Bhumika. Thank you, everyone, for your participation and valuable time. We are delighted to have today in this wonderful session. I would like to extend my special gratitude to our guest of honor, Dr. P. Bhinkat Raju, for delivering such a valuable lecture. I would also like to express my gratitude to our honorable guests, Dr. Bojan Dorin, Dr. Prabhakar Sharma, Dr. Karthikeyan Lanka, Dr. Uday Mandal, and Dr. Pulakeshwar Das. Last but not least, I would like to thank our convener of this webinar, Dr. A. Shahu, and to our coordinator, Bhumika Goel. And finally, I would like to thank our chairman, Dr. Bishwajit Roy Chaudhary, for providing such a wonderful platform for sharing geospatial knowledge in water resource management. Thank you, everyone. Thank you so much. And I would like to request everyone to fill the form for attendance. Everyone, please fill up the form for your attendance.
Hello? Office ma'am.
If someone is not able to access, please to send a request from there only, and save the link. The access will be granted soon.